Okay, perfect. Go ahead.
Yeah, so I can start now, Dennis. Okay, perfect. So yeah, before beginning, many thanks to all of my friends, family, and also my friends here in person to join here. I'm really happy to, after finally almost 3 years, to defend my thesis. So this thesis is entitled Impacts of Different Hydrogen Demand Levels and Climate Policy Scenarios on the Chilean Integrated Hydrogen Electricity Network. So let's see. So what is the main motivation for this thesis? There is really a huge momentum in favor of low carbon hydrogen in Chile, but also in many parts of the world. This is because hydrogen, to start from the beginning, this is a gas which, similar to natural gas, can be combusted to generate heat, or also, for example, to move an engine, to move a vehicle. And this is a gas that is particularly very good because of its high energy properties. So this is a way in which we could cost effectively replace fossil fuels, for example, in sectors such as aviation, long distance transport, shipping, and many others, where sometimes electricity alternatives are either non-feasible or too expensive. And in this case, hydrogen as an energy vector can be a good opportunity if it's produced with a low emissions process, so that it can, in practice, reduce emissions compared to fossil fuels. So about hydrogen, over 35 countries have published strategies, either published or in preparation until last year. And in fact, Chile is a front runner because Chile launched its strategy in the end of 2020, where they set out a target of 25 gigawatts of electrolysis, which is a technology to produce hydrogen using water and electricity by 2030. And this is a very big goal because it's comparable to the target that the whole European Union set out for 2030, which is 40 gigawatts. Also, on top of the domestic decarbonization ambitions that Chile has for hydrogen, the country outlined very important exports ambitions, which, for example, could lead to about 800,000 jobs by 2050, if the ambitions in the strategy are met. In fact, the Chilean government expects hydrogen to contribute with about 21% of the emissions reductions towards Chilean carbon neutrality by 2050 goal. So this is really a very important energy opportunity for Chile, both in economic development terms and also in decarbonization terms. So where does the potential for hydrogen come? Hydrogen, if produced with electrolysis, which, as I said, is the process to produce hydrogen with electricity and water, is about 50 to 90% of the costs of hydrogen. So if we have cheap electricity and also low carbon electricity, then we can have a very competitive low carbon hydrogen source. Chile, in fact, is a very good country for renewables. For example, we have about over 1,200 gigawatts of solar PV potential. Also, on top of that, we have over 500 of CSP, which is concentrated solar power potential. And we also have about 40 gigawatts of wind potential. This is all excluding the Patagonia. So we are talking about a very abundant and competitive renewable potential, which could enhance the country and enable the country to produce hydrogen in very large and also low cost amounts. So now, given this opportunity, we should find a way to plan for the ideal and the minimal cost system possible to take advantage of this important opportunity for the country. In that context, for energy systems planning, usually optimization models, which basically minimize a certain objective, in usually its total costs, subject to a different set of conditions that the system has to comply with. These models are usually used to plan energy systems and also to do some policy analysis on them. We can also see and say that there are many benefits of integrating hydrogen power networks. This is, for example, because electrolysis, as I said, uses electricity and water to produce hydrogen. But at the same time, hydrogen can be used, for example, with a hydrogen turbine to produce electricity. So this two-way interaction can enable multiple benefits by integrating both systems, for example, in terms of lowering costs, lowering emissions, and integrating more renewables. We can also say that the technology diversity is a challenge because when coupling both these systems, there is a huge portfolio of technologies to choose from. For example, variable technologies of generation, such as solar photovoltaic and wind power, but also non-variable like gas plants, coal plants, and many others. We also could have transmission lines for electricity, hydrogen pipelines to transport hydrogen, hydrogen carrying trucks, storage, hydrogen to power technologies, and many others. So this diversity calls for a very good model to plan for the best system. And lastly, we have some models that have been proposed that plan for integrated systems, which is planning for a system that considers both hydrogen and power networks together. But usually they focus on designing for one target year, for example, 2050 only, or they focus too much on one network, but maybe less detail in the other one. And in some cases, in some papers that do have some more detail in both and model the evolution of the system, they use a mixed integer approach, which sometimes is harder to solve, or also they omit exports or technologies that can be very important, such as solar thermal. In the case of Chile, we have also some studies that have been published. For example, Gallardo, Urtubian, Sauman, Armijo, and Filibet. They have published work that mostly focus on hydrogen production, not on the network as a whole. And there are some analysis, for example, from Osorio Aravena, that have published internet system analysis, but usually they have reduced geographical detail, which is they have very little nodes, up to 6 for the whole country, which is not much. And they also don't include hydrogen exports, which is very important for Chile, nor storage or transport, which could play an important role in their supply chains. And lastly, we also have that the Ministry of Energy of Chile has their own long-term power system planning process. But in their case, although they incorporate a very good detail of the power system, hydrogen is only considered as a pre-allocated power demand source, meaning that they define previously, before running the model, where the hydrogen will be located, and it's not an outcome of the model. And they also don't include hydrogen storage or transport modeling. So based on that, we have three main contributions. One is a methodological one, which is that we propose a new linear optimization model for integrated networks design, which is capable of allocating hydrogen and power production, hydrogen exports, representing energy transport and storage dynamics, a very diverse portfolio of generation technologies, all of this done with operational and policy constraints. We also, with that, carry out a case study from 2020 to 2050 for Chile that builds up and improves on the process of the Ministry of Energy. And we also, based on those results, we discuss and draw some policy implications in several different aspects. So what is, in a very short message, the main objective and what does this model do? This kind of model is called a capacity expansion planning model. And the main question it answers is, what investments should we deploy and how should we operate them to meet energy demand at each node and each time throughout our studied time horizon, also respecting a series of operational investment conditions at the lowest system total cost possible. So based on that, this capacity expansion planning model decides on several spatiotemporal decisions of investment and operation. For example, investment in infrastructure of generation, also transport and storage, for example. They also decide how these assets will be operated in terms of energy production, energy flows from one node to the other, storage, and among many other variables. And the idea, as I said, is to supply hydrogen and electricity demand at all times and in all locations, minimizing all costs involved. So now, to give you a brief idea before I jump into the equations, I will just describe this brief scheme to illustrate how this network works. We have several nodes, and every node is composed of a hydrogen part and an electricity part. The hydrogen part, as well as the electricity part, can have their own demand of hydrogen or electricity, their own supply, generation, and also their storage, which can be loaded or unloaded towards the node. And there is also like this two-way connection between both have nodes, because we can produce electricity with hydrogen to power technologies, but we can also produce hydrogen with electrolysis using electricity. So this interaction is what allows us to plan the system together. We can also then send some energy to other nodes, for example, in the case of hydrogen, via hydrogen pipelines, which is in Spanish tuberías, which can be used to pass hydrogen from one node to the other. And we also have some transmission lines for power. Now, very briefly, I will discuss the mathematical formulation of this model. So at first, we have an objective function that is the total costs that we seek to minimize, which is based on the fact that investments are modeled throughout years, and we also model the operation of the system using several days inside every year. So for this case, we model some target years, which means that we don't model the full horizon from 2020 to 2050. So we model 2020, 30, 40, and 50. And then we interpolate all the variables in between with a simple linear interpolation. Then also within those years, we don't represent every hour of the year. What we do is that we take some representative days, as they are called, to model just a small sample of some typical days that represent the operational dynamics that can be seen by the system in a certain year. So with those two dynamics, we model the costs throughout the whole horizon, both considering the investment costs throughout different years, but also the operational costs within each modeled year. We also have some energy balance and transport constraints. Basically, what these constraints do is that they ensure that everything that goes into a node is the same that everything goes out. So this is respecting the physical constraint of the system. We have that for hydrogen and also for power. And for both, we have some inflows that come from lines or pipelines. We have generation or production in the case of hydrogen. We have storage unloading and loading. Or we also have demand. So it's a very, very complicated and very includes very much many aspects in both types of energy vectors. We also here have modeled the demand. For example, if I produce hydrogen with electricity, how much electricity that needs, and at the same time, how much hydrogen is needed to produce electricity, for example. We also have some general generation constraints that model, for example, if solar photovoltaic or wind powered turbines can vary their output because of less sunlight or also less wind. So this captures the intradaily patterns of variable generation units like those. And this also models the technologies and the output of some technologies such as gas plants or coal plants that don't have these temporal variation details, and they only depend on their installed capacity to see how much they can generate. And particularly for CSP, which is, as I said, concentrated solar power, we have a specific set of constraints because this technology is a bit more complex than other ones. So this technology basically what it does is that it captures sunlight, thermal energy from the sunlight basically, and it can either store it in a chemical way, and then it can release that energy in form of electricity later. So this technology is a bit particular because it's basically we could say like an improved solar panel, because it can also store some of that energy to then release it later to the system in the form of electricity. We also have some storage constraints. These storage constraints ensure that, for example, the capacity of storage that I have at every moment depends on what I invested in before. And we also have, for example, here the inventories, which basically say that the amount of energy that I have stored now is depending on how much I had in the moment before, and the net discharge that I did in that moment before to see how much I have in this certain moment. Here, we model intradaily, which is from hour to hour storage decisions, but we also consider a seasonal approach for hydrogen, because hydrogen is a good opportunity to be stored seasonally, which is from months to other months, not within the same day only. So this only represents the dynamics for that kind of storage. We also have some investment and availability constraints. This basically says that, for example, the amount of generation capacity that I have in a certain year has to be equal to the sum of the investments I did in the years before until that year. We also here model that some technologies are already planned and committed to enter the system in a certain year. And also, for example, some plants such as coal power plants, which will be phased out, they will exit the system in a certain year. So this tries to incorporate all of those dynamics, and this holds both for generation, storage, and also for transport technologies. We also have some electricity reliability constraints. This basically ensures that enough reserves and backup capacity for the system is always present. And also we have an inertia requirement that ensures that enough inertia for the system is always present, to make sure that this is a very, very simple approximation for stability kind of constraint that we apply to the model. And finally, we have set an emissions limit, which basically with these constraints, we can limit how much emissions we allow the system to have. So with this, we can force the system to be zero emissions by a certain year, which is an interesting thing to analyze from a policy perspective. So with that model, we conducted a case study. So as I said, the case study goes from 2020 to 2050. With 4 target years, starting from 2020 and 10 years every step. We have 26 nodes and 28 transport corridors, over 1,000 power plants, and 12 representative days, which, as I said before, are the days that we are simplifying to model the operation of a whole year without having to model every hour of the year, because that could be too computationally demanding. And in this case study, we have technologies that range from a wide portfolio, for example, hydrogen pipelines, storage, electrolyzers to produce hydrogen, hydrogen-fueled gas turbines, and many others. And this model was implemented completely in Julia, the Julia language. For this, we have a network representation, which is basically a simplification of the national power system, which we have to specify doesn't run for the whole country. So this includes for the northern end of the country until Chilean island. So this does not include the Patagonia, for example, because those are isolated systems. We also have an energy demand projection, which basically shows us how much demand we could see annually for energy and electricity and also hydrogen. So here we have a base domestic demand of hydrogen, which is in blue. We also have some exports of hydrogen, which are in orange. And to the left, we have the demand in hydrogen units, but also to the right, we can also have the demand in electricity. Because as I said, to produce hydrogen, you need electricity. So to the right, we can see the chart that to the base power demand that the system would see without hydrogen, then we could add to that the electricity demand required to meet the additional hydrogen demand that is for example, for domestic uses, let's say heavy-duty fuel cell trucks, mobile uses in mining and industry, and also residential and industrial uses. And also on top of that, we could see hydrogen demand for exports, which could go into the international market. Basically, this chart shows that both energy for electricity and also for hydrogen could be quite concentrated. In fact, the metropolitan region and also the Antofagasta region could be very important hubs because of their industrial and also their mining activities in the case of the Antofagasta region. So they could demand a very good share, a high share of power and also of hydrogen. We also define some scenarios to compare with. So the baseline case is B, and in that case, we assume that the carbon tax is fixed from its present level, so it's $5 per ton of CO2. Then in that baseline scenario, we don't have any fully renewable system mandate, which means that the system does not have any obligation to be fully renewable. If it's not economical, it won't do it in that scenario. And also that scenario, the baseline scenario doesn't have any hydrogen exports. So that is what constitutes the B scenario, which is the baseline. And then on top of that, we modify some variables. For example, we add a higher carbon tax in some scenarios. In some scenarios, we also include fully renewable mandate for the system, for example, 2050 and 40. And we also, in some scenarios, include exports to see what variations these different aspects of the scenarios can produce in the system and in several variables of the results. So now, talking about that, let's discuss the results. First, we can see that the graph here shows the installed electricity generation capacity, and we can see at least three main messages. First, we can see that solar photovoltaic and wind technologies dominate the capacity mix, the total capacity in all scenarios. So if we see to the left in 2020, we had around 26 gigawatts of capacity installed for power generation, and that jumps to at least 95 gigawatts in 2050. And this capacity only grows, for example, with exports, which are the scenarios to the right. But in all cases, we can see that solar photovoltaic and wind technologies dominate with usually together about 65 or 70% of the total capacity. So we have to note that it is very clear that these both technologies would play a very, very big role in the system capacity mix. We also can see that hydrogen exports, as I said, they would also increase the capacity significantly, which would go in 2050 to over 120 gigawatts of capacity. This is a lot more than what we saw in the baseline scenario, for example, which was about 95. And this capacity, this extra capacity is explained because with higher hydrogen demand, you will need more electricity to produce it. Therefore, it is a bit obvious that to produce that extra hydrogen for exports, which are very important source of demand, then we could have also a lot more capacity installed. We also see that hydrogen exports and climate policies, in both cases, they increase CSP deployment. Those are the values in yellow. This is because CSP is a renewable technology that can also provide a more or less stable supply because of its storage capabilities. So in these cases, with high demand, then we can see that CSP also increases to provide more of a base load generation capacity that also in some cases was previously produced with gas. But this is showing that maybe CSP could be more cost effective in the long term, and also, of course, would produce less emissions than zero emissions compared to gas that is CO2 emitting. Finally, you can also see that in the hydrogen export scenarios, the three to the left, to the right, battery investments are less attractive, or we could say also even unnecessary. This is because hydrogen exports require more electricity to be produced, and because usually those hydrogen is produced in the sun in daylight hours, then there is no surplus electricity that usually is linked to solar PV technologies. So in the other cases, there are some batteries because we had some surplus electricity that was stored in batteries and then released again to the system, for example, at night. But in these cases, because of the higher hydrogen demand, it's a better idea from the model's perspective to use that extra electricity to produce hydrogen instead of to store it in batteries. So that's why we would see almost or practically no batteries in those scenarios, because that extra electricity in the sunlight hours would be better used to produce hydrogen instead of being stored as in a battery. Now about electrolysis allocation, we can see that comparing all scenarios, it is a very robust result that producing hydrogen almost exclusively, not fully, but almost exclusively in the north would be the most economic solution, both with and also without hydrogen exports. This is explained because most of the solar PV potential is in the north of Chile. So in this case, the model is saying that it makes sense to produce the hydrogen closer to where the cheapest electricity is, which is, of course, in the north, because of the high solar photovoltaic potential and also the CSP potential to a lesser extent. Also, regarding transmission line capacity, we can see that the model says that we would have a very, very important increase of this capacity. So we see that, for example, in the baseline case, we would see lines, or more specifically transport corridors, which can be aggregated lines. They would have over 20 or sometimes gigawatts of power transmission capacity per corridor. And that capacity in the hydrogen export scenarios could grow even almost to 60 gigawatts. So this is a very important result. Also comparing to hydrogen pipelines, because hydrogen pipelines usually don't surpass in our results 10 gigawatts. So we can see that as we would have transmission line capacities of over 40 in some cases, or even up to 60 gigawatts, the preferred way, not always, but in many cases, by the model will be to transfer energy via power lines, transmission lines, and pipelines for hydrogen transport would be left for some very specific corridors in the case of the system that we are simulating for 2050. Now, talking about generation by technology, we can also see that, for example, in 2020, we had about 36% of power generation via coal power and about 10% of gas. Because of the Chilean plans to phase out coal power from the energy matrix, we by 2050 wouldn't see any coal generation, but we would still have about 10 or 11% of gas. This is showing that, as I said, the baseline scenario has no additional climate policy and no extra or a higher carbon tax. This is saying that basically without any policy or tax, the system would still be economically efficient if we have a bit of gas generation. So this is saying that in a merchant scenario, we would still have some emissions because of gas generation, which to some extent would be economical to have at least a bit of it. But if we look at the scenarios, for example, with climate policies, then that gas generation is phased out because climate policies make gas generation less attractive. We can also see that, for example, in the case of hydrogen exports, if we see the H2 EXP scenario, which is basically the baseline scenario, but adding exports to it, so no additional or higher carbon tax, nor a fully renewable mandate, we see that despite the role of solar PV increases a bit, and also CSP, we would still have some gas generation. So in this scenario, with exports, we would have some gas generation still, and that gas generation would only be phased out if we have a climate policy that is a higher carbon price, or, for example, a fully renewable mandate for a certain year. Also now, continuing on the connection between solar PV generation and electrolysis, which is the technology, as I was saying, to produce hydrogen using electricity and water, we can see that electrolysis can benefit and can be flexible because we also have hydrogen storage. So having both technologies together means that I can basically decide when in the day it's more economic to produce hydrogen because I have the ability to store it. So I can, for example, produce a lot in the day, then store it, and then supply it to my consumer when the consumer demands for it. So this is a big advantage of having storage, because otherwise the electrolysis could be forced to produce exactly when it is demanded to produce hydrogen. But in this case, because we have storage coupled with electrolysis, then the model can decide when to produce electrolysis, when it's cheaper, and then to release that hydrogen to the node when the node demands for hydrogen. In this case, we see that in all of the scenarios, as we see in the daily profile there in blue, for all of the representative days which model the hours in a day, the electricity production for electrolysis would follow a solar PV pattern very strongly, which is showing that the system deems it optimal and cost efficient to produce hydrogen with electrolysis, mostly or almost exclusively when there is sunlight, because as I said, there's a very important aspect of the price of hydrogen, of electricity. So a solar PV electricity is so cheap, the system finds it convenient to produce hydrogen mostly when there's sunlight available. Now, regarding system costs, we can see that, for example, both climate policies and also higher hydrogen demand via exports, they increase system costs because they demand either for more investments or at least like a higher operation of the system. So climate policies increase the system cost by up to 13.9%, and the exports by up to 53% in this case. We also see that the system emissions have several aspects to analyze. For example, hydrogen exports on one hand decrease the average electricity emissions intensity, which is basically a measure of the total emissions of the system divided by total generation. So it's like a measure of how much carbon content there is in every energy unit generated. So we can see that because that additional electricity to meet the additional exports of hydrogen demand is met via solar PV mostly, so that decreases the average emissions of the system, which is why we say here that they decrease, the exports decrease the average electricity emissions intensity. We also see that setting intermediate emissions reductions incentives, for example, carbon prices or emissions limits, they incentivize or force to reduce emissions in the path to 2050, and in both cases they reduce cumulative emissions by up to 55%, which is the total emissions in the whole horizon, not only a specific year in particular. Now, before concluding, I will discuss a bit on electricity prices. So in this case, we can separate the analysis on end users, the typical end users of electricity, and also the price that electrolyzers would perceive because of being supplied with electricity. In both cases, we see that climate policies would not significantly impact the prices in 2050. For example, the variations in end users and also electrolyzers are minimal, less than $2 or $3 per megawatt hour, which is megawatt hours is a unit of electricity, of energy. But in the case of hydrogen exports, which could mean that demand of electricity increases by almost 60% because of that additional demand. In this case, hydrogen exports cost almost doesn't change or even decreases a bit the typical consumers' electricity prices, because that increase in system costs is met in the electrolyzers prices. So let me explain this. Electrolyzers can be flexible, so they can basically, because of storage, they can decide at what hour of the day it's more convenient to operate. So for sure, because they depend a lot on the energy prices, electrolyzers seek for the lowest cost hours, which usually are in the day. In this case, as they can be flexible, they can move towards the cheapest hours, and therefore, when they begin saturating those hours, they themselves feel the effect of increasing costs, and therefore they don't affect the end users because the end users are not changing their behavior. So in this case, we see that because of the flexibility of electrolysis, the increases on system costs are mostly perceived by electrolyzers in terms of electricity prices, but end users would not be very affected and could even sometimes decrease on average in some cases. And now, finalizing with the hydrogen price outlook, we see that adding hydrogen exports, which in terms of hydrogen demand increases almost by 300%, they result in hydrogen prices growing, in this case, by up to almost 40% in 2050. And this is because, as I said, for electrolyzers, the prices increase. So because electricity is so important for hydrogen prices, then also that triggers an increase in hydrogen prices. So this is saying that it's very important to take into account that if electricity prices increase, then electrolyzers will probably have a higher price, which would be reflected in their hydrogen production costs. So yeah, now to finalize and to summarize my research. At first, we can show that we carried out a 2020 to 2050 a Chilean case study, incorporating different levels of hydrogen demand and also climate policy scenarios. We conducted this analysis by using a new linear capacity expansion planning model for integrated hydrogen power networks that incorporates exports, energy production, transport and storage, reliability constraints, also seasonal hydrogen storage, as I discussed, and they also incorporate many other operational and policy aspects. By 2050, as our first result that I want to discuss, our baseline scenario that I said doesn't have any hydrogen exports, doesn't have any additional fully renewable mandate or carbon tax. This baseline case suggests that the system would be reducing emissions by 2/3 in 2020 by 2050 compared to 2020 without any additional measure. But if we're seeking for additional emission reductions, we would have to implement either, for example, a carbon tax or a higher carbon tax or some mandates to reduce the emissions and therefore decarbonize the system deeper by 2050. We also now on to the last three conclusions. We see that carbon taxes and also 100% renewable mandates reduce annual emissions by 2050, and also the cumulative emissions throughout the whole period. In this case, the cumulative emissions reduce themselves by up to 55%, but they come at a premium, which means that they could increase the costs of the system throughout the whole period by up to 13%. Very importantly, we see that incorporating hydrogen exports would enhance renewable deployment, particularly CSP, wind, and solar PV deployment, while not necessarily increasing prices for average consumers of the system. They would also decrease the average lower emissions intensity. And as I discussed, the increased energy supply costs would be mostly perceived by electrolyzers, which would in turn affect the hydrogen price outlook. And finally, I can also state that based on the results of the model, it could be economically convenient to allocate almost all of the production of hydrogen in the north, including and particularly in exports. And this can result into significant land and water use needs, which possibly could translate into some socio-environmental impacts. For example, if we were to need significant amounts of desalination to supply that extra water demand for the system. So that was my presentation. I'm really happy to have the opportunity to present this to you, and yeah, looking forward to answering all your questions and comments.